Okay, so we know how to move from a carbonyl to a hemiacetal. Okay, so let me call this R prime prime. In fact, R prime prime, R1, R2, R3 might be the same or different. Okay, and to do this, we said we need an acid catalyst, which will give us that hydrogen, and an alcohol, which will give us the RO, because this is going to be lost in the mechanism. So the shortcut is if you start with a ketone or aldehyde, okay, the RO is added and the carbonyl is converted to the alcohol. That's the shortcut. Now because you have the OH and OR, this is called hemiacetal. Okay. Now the hemiacetal can go straight to an acetal. The hemiacetal can go straight to the acetal if you have excess of the alcohol. So I'm adding my R prime 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 the second time. So this will be the second equivalent. Okay. Still, you're gonna need the acid catalyst. This part right here, now it's this part right there. So now you have your OR group, two of them. So now it becomes an acetal. Specific example. So let's say you start with acetone, okay, and then your alcohol of choice is ethanol. You add it the first time, so you get OH and the ethanol part. Let me use a different color. So this is the ethanol part. Okay, so this OH falls off like I did here. This acid here would be this hydrogen here after the carbonyl opens up. I'm just giving you shortcuts. So this is a hemiacetal. For the mechanism, go back to the lecture. Now, once you have your hemiacetal, it can react one more time. Okay, so the hemiacetal can react one more time with a second equivalent of the alcohol ethanol. Again, I'm just giving you a specific example here. So second equivalent, okay, the second molecule, second equivalent of the alcohol reacting. After following the mechanistic steps, you'll have the two CH2CH3s attached to the carbon of the carbonyl, and that's what we would call an acetal. So in red, this was what you started with. Let me see, I don't know why it's not picking up red. Want you to see the difference. We need the red pen. Alright, so this was your original molecule. Now you have the two OR groups. Okay, R group is the carbon containing group. So this is an acetal and this was hemi because you have an OH, OH and OR. So now notice that these are not rings, so you can do the same for rings. Okay, so again, remember this is just formation of acetals from hemi and usually follows SN1. So you can do the same for rings. Notice that this is a carbonyl compound. You have a hydrogen there, so it's still generally RR, but in this case one R is hydrogen, the other is a carbon that goes all the way round like this. So this is an aldehyde. On the same aldehyde you have an alcohol. Okay, here we are adding an alcohol. We are adding alcohols onto the carbonyl containing compound, but here the alcohol is on the same structure as the aldehyde. So in this case you have both the electrophile and the nucleophile on the same molecule. So remember what we said, carbonyls are not reactive, so first we would activate it by mechanism. So you're gonna end up with a positively charged oxygen, your OH is still there, and then now your oxygen of the alcohol will take the role of a nucleophile to attack the carbonyl. The pi bond opens up, you're going to make a 6-membered ring. Okay, and an OH up there. So the bond here is this arrow attacking the carbonyl. The oxygen here now it's neutral with 2 lone pairs, but this oxygen right here is going to be positively charged because it's used its lone pair. Otherwise you can do your formal charge calculations. Remember this bond is formed whenever the lone pair attack the carbonyl. Alright, so now molecules, organic molecules don't like being charged, so one can use an alcohol in the flask, let's just generally say a base, to remove this hydrogen and neutralize the oxygen. The alcohol can take the role of a base, like I said, to remove the hydrogen to neutralize the oxygen. So let's just use B generally. It can be water, it can be alcohol. So you're gonna get, once the hydrogen is gone, you're gonna get 2 lone pairs here. There are still 2 lone pairs there, and that's your product. Notice that this side is your OR group and this is a OH group sharing the same carbon, so it's a hemiacetal. This can go one more step. If now you come with a different alcohol, let's say methanol for example, the OH will be turned to OCH3 because obviously this hydrogen of the alcohol must be lost as it was lost here in the last step, which we always call proton transfer. Okay, so the OCH3 will replace the OH, and now you have OR on this side, you have OR on that side sharing the same carbon, then it becomes an acetal. Okay, so sugars like sucrose, fructose, maltose, they do this naturally. Very common for 5-membered rings and 6-membered rings where you make rings. So if we were to do the same mechanism, this time not on 2D but 3D, using a chair, okay, so in presence of an acid catalyst where this will be bonded to the acid, the lone pair would attack here, that opens up, this oxygen will have its hydrogen still, and then next you'd use a base to take out this hydrogen, neutralize the oxygen. Then you'll end up with your chair that's a hemiacetal because you have an OH on that carbon and you have an OR group on the same carbon. So OH and OR sharing the same carbon, you get a hemiacetal. So the mechanism is the same, very same. Okay, so let's do it. So you use a lone pair on oxygen to attack the carbonyl. The pi bond can open up, picking up the H plus. You get this charged oxygen, and then you use any base, let's call it B lone pair, take out the hydrogen, neutralize the oxygen. Now the oxygen has two lone pairs, and yes, you now have a hemiacetal. This is an extract from your book. Okay, so it's hemi because the carbon bearing the OH also bears the OR group, so it's hemiacetal. Okay, now one would want the B groups equatorial, so you want to refer to stability of chairs. In the chapter we talked about chairs. I don't know if it was chapter 3 or 4. Alright, so ketones will react in the same manner because here this is an aldehyde. Ketones will react in the same way. So again, you'd use your lone pair to attack the acid catalyst because the carbonyl is not super active. That's why we always use the H plus. Sorry, we no longer have two lone pairs. You only have one lone pair after using it to attack the hydrogen, and this gets a plus charge. So now you have your carbon groups there because a ketone, remember ketones has carbons across the carbonyl. And now moving forward, your alcohol will come to attack that carbon of the carbonyl because it has partial positive charge. The pi bond opens up, so you get OH. Okay, and the alcohol that attacked, so let me change the color. The alcohol that attacked still holding on its hydrogen. The oxygen is left with one lone pair. You have a plus charge on it, and then let's see. So to get the hemiacetal, one would use a base or another molecule of the alcohol to take out that hydrogen. That's how you get the hemi. Again, this is hemiacetal because the OH and OR are sharing the same carbon, is half the acetal. Now, to move forward to get your acetal, you do the same thing that you did before. So the OH oxygen will be used to grab the hydrogen because remember you have to activate your OH to be a good leaving group. If it leaves without activation, it makes OH minus, which it's a strong base, and strong bases are poor nucleophiles. So we don't want it to leave as OH minus. We want it to leave as a neutral molecule, in this case water. So it accepts the hydrogen, it used its lone pair oxygen, gets the plus, and now we can lose the whole thing as water. So you get your carbocation intermediate. Okay, so carbocation intermediate, in which case now your alcohol is very much happy to come and attack the second molecule of the alcohol. Okay, we'll use its lone pair to attack the carbocation. Then you're gonna get your alcohol with the oxygen positively charged, bonded to the rest of the structure of the carbocation. And again, organic molecules don't like being charged, so one can use a base or a third molecule of the alcohol to take out this extra hydrogen. you neutralize the plus charge on the oxygen. That's just an arrow. I'm just drawing the arrow from the bond to the oxygen. Let me clean it up. Okay, let me use a different color. So this bond, the 2 electrons end up on the oxygen. So now you'll have 2 lone pairs here. You had 1. And of course that's OR. Now you get an acetal because the OR and OR are sharing the same carbon. Okay. An older convention called this a hemiketer because it came from a ketone. But let's just stick with hemiacetal and acetal. So what the aldehyde can do, the ketone can do. But aldehydes are more reactive than ketones because they are less sterically hindered. The carbonyl is less sterically hindered. So we usually use acetals up as protecting groups, and I'm going to explain that. So the problem is that if you want to do a reaction without affecting a carbonyl group, if you are using a nucleophile, let's say you are using a nucleophile, right? And you want to do SN2 here. The problem is that this nucleophile will not just attack this place. The nucleophile can also attack the carbonyl. So to stop the nucleophile from attacking the carbonyl is to make sure you don't have a carbonyl. You hide it using what we call a protecting group. Okay? So in this case, one would want to protect the protecting group in form of an acetal. Now, let's say you are doing a reaction that we call Grignard reaction, where probably you have an R group. For me, let me say CH3. You have magnesium and a halide. X is a halide, bromine or chlorine or iodine. So whenever you have a Grignard, this can be taken as CH3 with a lone pair and a negative charge. Like this is just a cation. That's just a cation fragment. It's a spectator ion. So this becomes a nucleophile. So if you have CH3, negative, that can be used as a nucleophile, right? To attack the Cl and Cl fall off. So in this case, I would have put the CH3 here. But that does not only happen. Still, this aldehyde will be attacked by the CH3 minus if you are doing Grignard. And in that case, you will end up with this molecule. Okay, you end up with that molecule. So the CH3 will add on the aldehyde, this picking up a proton in the solvent, and the same CH3 can attack the chloride by SN2. So to prevent that, we usually protect the carbonyl if you only want SN2 on the halide. Okay, so how do we do that? Okay, so remember how we said that alcohols, 2 equivalents of the alcohols can add across the carbonyl. So generally, let's say you have this, and then I add 2 equivalents of this alcohol. What would you expect? One would expect an acetal. So for example, you'll expect the OR prime there and OR prime there. The hydrogen is still there. That becomes an acetal because you use 2 equivalents. Now what if the 2 alcohols, instead of 2 equivalents, what if the 2 OHs are on the same molecule? What happens is that these 2 oxygens will cap the carbon of the carbonyl. So see this carbon right here is this carbon here, and then these 2 hydrogens will be lost. So this O CH2CH2O is O CH2CH2O. That's called what's it called, a ketal, I think. but it's a type of acetate. So this is your aldehyde that's protected. It's no longer an aldehyde. It's still an acetate. It's still an acetate because you have OR group on the top and OR group at the bottom. But we are using it to protect the aldehyde. This molecule, the diol, does not react with the chloride. So now before I do much of this, let me again give you, I'm not going to discuss the mechanism, I'm just giving you the shortcut on how to protect carbonyl containing groups. Okay, so let's say you have this one, you have this carbonyl group generally, and I react it with 2-carbon diol. So let me get rid of that. So I want to react with a 2-carbon diol. Your shortcut, it's usually in presence of an acid catalyst anyway because you want to activate your carbonyl. Your shortcut is forget about the carbonyl and just use the oxygen. So this and this will go and the oxygen will go. What does that form? The byproduct will be water. So all we are using now is what's left on this structure O, R group O, and then sticking it where the carbonyl was. That's your shortcut, and that will make life easy for you because it's more complex than this if I have to do the mechanism. So that will be the product. Remember, this H2 and O, so the O is this guy, the H2 is that and that, so we use the rest of the piece to put on there. So specifically, if I have acetone, no, let me use isopropyl, and I'm reacting it in presence of an acid. Let me first draw the skeleton. So let's say I'm using the two-membered, the 2-carbon diol. So again, I know the H and H will not show up on the molecule, the oxygen and carbon will not show up on the molecule. Only the rest of the structure will be clicked onto the molecule because the carbon here must have 4 bonds. So you get a cyclic acetate. So now what if I have a bigger carbonyl structure, like let's say I have that, and I have a bigger carbon diol. So let's say I have 3 carbons to the diol. It's the same thing. The OH and OH will be lost. Of course, here you lost water. Those will be lost and forms H2. And the oxygen and carbon should no longer be there. So I will need a 3-membered crown protecting group. You see, carbon, 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 those are 3 carbons. 1, 2, 3, 1, 2, 3. And these 3 will be joined onto the carbon structure of the carbonyl skeleton. So to be joined there. Okay, so there's a carbon right here. So generally drawing it, I would have drawn it like this. That's still a cyclic acetate. Okay, so these are protecting groups, of which if I want to go back here, it's very simple. I just add an acid catalyst. That will be the protection. So again, if I want to move from here back to where I started, I just add an acid catalyst. That will be the protection. So moving forward is protection, moving backward is the protection. So after reaction, probably I was protecting it to do something else on the molecule. I can get back my carbonyl. Okay, so moving backward is the protection. and it's usually in presence of HCl, like think and heating. So I've given you the shortcuts. Now let's move forward. So now that we don't want our Grignard to react with the chloride, because we said if you have this aldehyde and you do your Grignard, let's say you're doing your Grignard with MgBr, this CH3 becomes a nucleophile generally. The MgBr becomes positive. So this CH3 can attack the Cl by SN2, and in that case the CH3 replaces the Cl by SN2. Okay, but that is not the only reaction. This CH3 can also decide to attack the carbonyl picking up a plus, and in that case you get two products. So you got the SN2 product, and you're gonna get the other product where the Cl might survive, and you get your OH. After the CH3 attacks the carbonyl picking up a proton, you get OH, because the pi bond opens up picking up H plus to the oxygen, get OH. We still have the CH3 that attacked is right there, and then you have the hydrogen. So you get mixtures. So to avoid these mixtures, one would want first to protect the aldehyde using a diol. So you get the acetal like we did on the previous case. The Cl survives because the diol does not attack the Cl carbon. And now we can do our Grignard, because now the Grignard will no longer attack the carbonyl that used to be here. It's protected, it's covered, it's masked. So remember what I call this? I call this a Grignard reagent. Okay, after the scientist Victor Grignard. So the R group is usually taken as a nucleophile. Just disregard the MgX. This is taken as a nucleophile. Now this can be used to do SN2. The Cl falls off, you get that. Your aldehyde is still protected. So if you want to get it back, what do? You deprotect. Sorry, this is a typo, this should be R, because we're just using this molecule here. Now we want our carbonyl back, which we started with. So you deprotect, you get back to your aldehyde. So in this way, you've made sure that you are not getting this byproduct. You're only getting this. So first, you take your molecule, take your original molecule, protect the aldehyde that will cause side reactions, and now do your actual reaction. In this case, it's SN2. On the other side of the molecule, the Grignard uses its R group to attack that side. You get the R group here, which could be a CH3, an ethyl, a ring. And now you want your aldehyde back, so you take this product, right, and then add an acid catalyst by deprotection. So this is the protecting step. You lose the cap, you lose the protecting group, you get back your carbonyl. The mechanism for this step, I think, is way beyond your scope. Alright, so we've been reacting carbonyl compounds with alcohols. If you react it with water, there's no OR added, it's just gonna be an OH. Okay, this is the OH added from water. Okay, so you're still gonna need an acid catalyst. So whenever you have two OHs, you call that geminodiol. That's what gem, not the gem, the mineral, it's the geminodiol, because the OHs are on the same carbon. Okay, the thing is, these are reversible. You can still lose the OH and go back to the carbonyl. Alright, so I've mentioned about Grignards. So usually if you have to use Grignards or what you call cuprates, those are organometallic reagents because they contain a metal. For example, Grignard contains a metal. Or if you are to use a cuprate, which looks like this, still you're using copper, Cu. That's an organometallic reagent, but I think for your case we'll just cover Grignards as an example of an organometallic reagent. They are strong nucleophiles and also strong bases because I said, for example, if you have CH3, MgCl or Br, usually this bond is very weak and it breaks towards the carbon, so one will get CH3 with a lone pair negative and you'll get MgCl with a positive charge. This will be the nucleophile and it happens to be a strong base because carbon is less electronegative. So in this case, the main interest is the R minus when this bond is disregarded, and then Mgx plus becomes the spectator ion. So this is your interest. That's a strong nucleophile for Grignard. So whenever you react an aldehyde with a Grignard, you get a primary alcohol. Let me give you an example, specific example. So if you have this aldehyde and we are reacting it with a specific Grignard where the R group is a methyl, so I would again only consider the CH3 with a lone pair negative charge. That's what the Grignard gives, as I explained here. So you use this to attack the carbonyl. This opens up picking up a proton, so you'll get your OH. After the carbonyl opens up picking up a hydrogen, you get OH. This hydrogen was there originally, and then the CH3 is now attached onto the carbon of the carbonyl. Okay, so aldehydes can give you primary alcohol, secondary. In this case, we have a secondary alcohol. How do we get a primary? It's from formaldehyde. Formaldehyde is the babiest aldehyde. It has two hydrogens. So you can imagine doing the same reaction with CH3MgCl. Again, the MgCl will be positive, the CH3 R group will be negative. Use it to attack this. This opens up, picking up a hydrogen, you get OH. So you'll have your two hydrogens, alright. The carbonyl opened up, picking up a hot OH, and then the CH3 will be down here. This is a primary alcohol because the carbon bearing the OH is bonded to one R group. Okay, remember what we said about primary alcohols. Okay, one R group. Secondary alcohol, you see how here this has two R groups. Secondary alcohols will have two R groups. And of course, tertiary alcohol will have three R groups. So let's say you have acetone. This time my Grignard is CH3, CH2, MgX. Okay, MgCl. So I told you that we usually disregard the MgX. It's just a counter ion because that's just gonna be MgCl plus, and then this part will be CH3, okay, CH2 minus. So I'll use this to attack the carbonyl by SN2. This opens up picking up a hydrogen, so I will get my CH3, CH2 bonded to, I'm just trying to draw the product, bonded to the carbon bearing the two metals and the oxygen picking up a hydrogen. So this part in red used to be our acetone. This part came from the Grignard reagent. It came from our Grignard reagent. So now you see you have three R groups. Three R groups means that you have a tertiary alcohol. So ketones will give you tertiary alcohols. Other aldehydes will give you secondary. Formaldehyde as explained here will give you primary alcohol with Grignard. Okay, so again, in this Grignard reagent, I'm considering only the R minus because MgX is just a spectator ion. These R minus attacks from the back, that opens up. You see how you have 2 lone pairs? So now you're gonna have 3 lone pairs, and those 3 lone pairs will take one of it to react to accept a proton, because hydronium ion is simply proton donor. Okay, so that's why I say this can open up picking up a proton. This is what I meant. You pick up a proton, you get an alcohol. So in this case, that's a tertiary alcohol because you started with a ketone. Okay, so you see how this step number 1 you do the Grignard, and then step number 2 you acidify. So we can list the 2 steps in under one arrow. So what is represented up here is just what's down here. The second step here, it's just protonation of the alkoxide. And this one here is the alkoxide. Of course, you see the O minus there. Okay. Now, organolithium reagents is same concept. Specifically, if you have, let's say, a CH3 and a lithium, of course, lithium is a metal, will be plus charged, the CH3 will be negatively charged. Just like Grignards, this is what we want. Just like Grignards, this is what we want. We disregard the Li+. This bond right here is weak or ionic, so you would say. So let's use this to attack from the back. This opens up. You had 2 lone pairs. Now you have 3 lone pairs. And then again, hydronium ion is just a proton donor. You get an alcohol. So in this case, you're getting a secondary alcohol. Why? Because you started with an aldehyde. So again, step number 1 was the nucleophilic attack, which is SN2 version. Step number 2 is protonation. These two can be written as one. Okay, so you end up with secondary alcohol. Okay, one can also add an acetylide group. Okay, so you have a lone pair here. That's what gives the negative charge. Okay, alkynes can be used as nucleophiles. You're attacking your aldehyde. This opens up. You still get the alkoxide, and then that's a proton donor. Use a lone pair to accept the proton. So again, you end up with a secondary alcohol. So we are using this acetylide group as a nucleophile. Okay. So again, you have 2 steps. That was step number 1, nucleophilic attack, SN2 version. And then you have protonation. We can combine those 2 steps, protonation and nucleophilic attack, under one arrow. So you'll first do step 1 and then do step 2, which is protonation.